Okay, welcome back. So in the last module we were looking at, say, if you have a different chemical spill, what are the different properties which kind of dictates where the chemical will be. So those were since again those if you remember from this life cycle impact assessment and all, we were using those information to make those impact assessment. So now we will move towards a little bit in this particular module we'll do a little bit something I would say, although we have talked about it, but we may not have dealt in this particular topic in great detail. We have so far we have been talking about that how to measure the sustainability parameter. So that's life cycle analysis is used as a sustainability parameter. Now we'll look at when we say something is a green and sustainable material, what does that mean? So once the different parameters that we use, and then we can come up with something which is the material which is more greener. Greener means environmental friendly. So that's what we will try to do in this particular module. So let's get it started. So when we, as an engineer, we have to use material. We have, whenever we design something, the material is needed, and whatever like a material that we use, if it has lower environmental footprint. And how will know whether it is lower environmental footprint? We already know how to do LCA. We have already covered that over last 4 or 5 weeks. So if it has a lower environmental footprint, and that of course will have when I said lower environmental footprint means lower natural resources use footprint as well, and that kind of goes into this concept of circular economy and all that. So so if it's a to make this engineering design sustainable, we should use material which is has lower environmental footprint, as well as of course lower natural resource. So let's use less of that. So when we try to do this material footprint, it's not very straightforward. One part is of course looking at the LCA part of it, and then we have to look at in terms of their abundance. If you remember in that LCA exercise when we are talking about the resource acquisition, mining and all that, so when we talk about the mining, it depends on how much of that material is really available with Mother Earth, then only we'll be able to mine. So we'll talk about those kind of stuff which goes there. So we'll look at some of these 3-pronged approach to look at the footprint of material in this video as well as the next video. So those 2 videos will go over this green sustainable material part. So again some of these slides are too boring in terms of too much of a text. Don't try to read line by line as you are watching this video, but this is, again, as I said, this is for your reading material. This is just for your reading material, and you can read it later on when I give you the PDF of this. So but the bottom line is a material has to be extracted and purified, which we talked about that our mining friends do that for us, and that's our first component of the footprint. When we talk about this environmental footprint, that starts from its resource acquisition phase, where the material has to be mined and it has to be extracted. So that's the first phase. Then the material will enter the production system. Once it enters the production system, it can be reused, it can be reused, it can be recycled, and then a lot of energy and other resources will be involved. That's the second component of the footprint. Then later on, when the product is disposed, then we need to look at its environmental fate, persistent human health impact, which kind of part of it we talked about in the previous module, how to look at that. That's its third component of the footprint. So this is the 3-pronged strategy. So something could be very bad in the mining phase, something could be very bad in the mining phase, but they are okay in the second and third phase. So we have to look at the whole totality. So what has been happening so far, whenever we do this environmental impact kind of environmental impact studies, we don't look at this 3 part together. We look them in separate, just by themselves, and later on we realize that okay, it does very well in this particular area, but does very bad in terms of its mining activity, because it has a long environmental footprint over there. So one of the simplest approach in terms of doing that, so we will look at the 3 part, that environmental footprint of the material extraction. So one of the simplest thing for that to do it is we have to find out whether the material is scarce. When we say scarce, means the material is not available too much. The natural abundance of this material is very less. So some of the elements are are available in a large scale. So, for example, we have oxygen, silica, aluminum, iron, calcium, magnesium, potassium. They are available. All these elements are present at greater than 1% abundance. So, they are over there. But some of these widely used elements, for example, silver, tin, antimony, they are available in a very low concentration, and that kind of tells us. Even you can use your common common sense. Like when you look at the price of certain of these heavy metal, the pricier when something is very pricey, that means their abundance is very low. So gold, for example, silver is, you see, silver is much less costly than gold. So gold is costlier because the gold's abundance is much less than silver. So it's the abundance part. So in terms of the material extraction and refining, so there are environmental footprint associated with that. So we have to look at that part in terms of its impact. So there are different elements which has different kind of like a abundance part is present over there, and as you can see, this particular table, the mass abundance has been provided to you. So if we start from the bottom of the table, which is over here, this is a 3 as we go into the bottom part of the table, gold, platinum, silver, mercury, indium, palladium, bismuth, cadmium, antimony, molybdenum, arsenic. These are available at a very low concentration. Gold 0.004 ppm, as opposed to if you go to iron, for example, iron we had 5.6% of iron. So in that case, that's why gold is so expensive, because there are so less gold is available with Mother Earth. Had it been some other elements which is available at a lower concentration, probably that would have been more expensive than gold. So there will be things which are so based on their abundance, that what you see. So something which is at low concentration already, once we are mining it, mining, and at some point of time we will run out of that. So today, if you are mining, say 100 kg to get 1 kg of certain elements, tomorrow you may have to mine 1000 kg to get 1 kg of that element, just because it's the proportion is going down in the Earth's crust, because they are rarely available. So that's why many of these are also called rare earth metals. So similarly, as you can if you look at the previous table and this graph, you will see a correlation that more the abundance, of course, more are those metals that we are using. Iron, aluminum, copper, manganese, we use them a lot because they are available in lot as well. But that's not always the case. But in general, you see the annual production rate for use in comets. So that's, yes, in general, more the abundant, we use more of those element. Gold is used less, silver is used more, as we can probably see over there. Then arsenic is over there. So based on their abundance, you see different elements present over there. So, but what does all these mean? So let's look at an example. So kind of try to understand what does all these really mean. So if you are if you look at the abundance of material in the Earth's crust, so how much tons of the material, that's basically ton of material available with Mother Earth. And then we try to compare with the annual use of the material, like in tons per year, how much we are using it up. So approximately we can take a mass of Earth crust as 2 times 10 to the power of 19 metric ton. This is the mass based on 40 kilometer thickness of the continental crust and 3 kilometer thickness of the oceanic crust, and with an average density of 3 tons per meter cube. So if you take the average approximate mass of the crust as 2 times 10 to the power of 9 metric ton, based on the previous two, this table data and this graph data, if you try to do for some of these elements, for some of these elements, if you can see here in terms of its which one is showing more abundance, as you can see in this particular table, this iron, phosphorus, nickel, zinc, copper, and silver, for these three, they are at different levels, so that's why they have been picked up. So abundance in crust from that particular first table that we looked at, and then the uses per ton is in the second table. So based on how much we are using, how much it is available, if you do the math, we have around 10 to the power of 9 years of iron left. We have 10 to the power of 8 years of phosphorus, more of the same, around the same for nickel as same as iron. Zinc and phosphorus is similar. Copper and gold is at around similar, like 10 to the power of 7 of years. So that this scenario, it's assuming that whatever is there in the Mother Earth, whatever is present in the Mother Earth, if we can extract each and every of those material, so we have so many years left in terms of the usage of that material. So all the material can be extracted, which is not always the true, because the concentration becomes too low later on in some of those mining areas, and then they become too costly to extract them. So but there is a relationship between the total crust abundance and economically extractable deposits. So this is what is the totally extractable deposit, like how many years it will go. But there is also a term in terms of the total crust abundance and economically extractable deposits, so that we call reserves. So on average, only in 1 in 10 to the power of 7 to 10 to the power of 9 tons of an element is economically viable reserve of that material. So that's although you see a lot of things, so it's not that much whatever you see in terms of the years. We don't have that many years of all this material, and that can be usually expressed in terms of a graph which has been put together almost 2 decades ago, slightly more than that, and that's the relationship between the total crust abundance and the reserve. So as you can see, on the x-axis we have the reserve, and on the y-axis we have the abundance in crust. So how much is really available in terms of different elements we have, and out of this what can be extractable. So that's is out there, and you see 2 lines over there, and those 2 lines are based on different technologies which is out there, and so some technology is more efficient, we can probably extract more. So based on the technology, so this basically gives us a range. So this path is actually a range for us which we can use. So and as you can see for some of these iron, aluminum and other stuff which we use a lot, we see that they have we have higher reserves of that. Something which we use low, we have lower reserves of that, and it's very difficult to find out. Oil and coal is also over there, which will actually outside of this particular graph. So that's kind of gives you an idea about the total crust abundance as well as the reserves which is present, which was put together by Kessler in 1994, and we still kind of use that stuff. So in terms of if you look at ratio of abundance, so kind of looking at now the same problem, if we start looking at what is the economically extractable resource and how much use per ton we have for these different elements. So earlier we were using at the earlier table, earlier problem that we looked at, we were looking at what if the entire of this element present can be extracted. But now we are looking at what is the economically extractable resource, not the entire one, and we are putting their usage next to it. And then on this third column, if you do the math, so it's very simple math. So as you can see, for economically extractable, for the first element, which is iron over there, and for that I hope you can see it. I'll just make this table a little bit smaller so you can see that. So in terms of for the iron, if we have the economically extractable resource as 230 million, more than million actually, 10 to the power of 9 tons. That's the extractable resource. Use per ton per tons per year is this much. That means that we have 190 years of iron left. We have 100, and this data is based already around 10 years, 15 years old. So we can say around 180 to 185, 175 years of iron we have left in terms of its abundance. If we keep using iron the way we are using right now, if we don't recycle any of this iron which is available, and if we don't improve our recycling rate, 200 years from now we will not have any iron left with us to use. So similarly, if you look at the others, silver, we have 17 years worth of silver left, copper 200 years, zinc 152 years, nickel 100 years, antimony only 10 years, and SN is only 19, which is tin. So So that, what does that essentially tells us? This essentially tells us that we need to start either improving our method, improving our process, so that we can make efficient use of these elements that we have, so that we can increase these years. Because if you remember from the very beginning of the class, our focus in terms of this sustainability is making use of the resources today, and with the plan, so that our future generation can enjoy the same resource. But as you can see in this table over here, that's really not going to happen unless we change. If we keep on working the way we are working in terms of this linear economy, where we just make things and dump it into the landfills and other places, that's not going to happen. We have to improve the recycling rate. Many countries, Western European countries, some of the North American countries, they are working on the recycling rates, but in the developing countries, a lot of informal recycling is being done, but still we have to improve on our recycling process, because recycling is being done today, but it's not being done in a very, I would say, it's done in a crude way. There is a lot of wastage, and there are lots of environmental footprint in those recycling process. So we need to really look at this recycling in a much bigger way, so to improve this number of years that we can still use these metals. And then of course we need to look for better technology. We are making lots of plastics now, and some of these could be iron has been replaced. In many of these, iron is being replaced by plastics, as you can see in your computers, laptops, cell phones, and other stuff. So that's why they get lighter as well. So that was kind of to give you some idea about that. So although the total amount of material available in Earth's crust is sufficient to support current rate of extraction indefinitely, as you can see in the example 1, several 10 to the power of 9 years, 10 to the power of 8 years. The second example shows that the total amount of it's present in high concentration, which is economically recoverable, is much lower. So this is because the energy and other resources required to mine, they purify the material for use. So that's where that this concept, the other concept comes, which is known as the Sewood relationship. This Sewood relationship, this concept was, what is the cost of the material is largely determined by the cost of extracting and purifying the raw material. So although it may be there with Mother Earth, how much cost goes into extracting that material and then to purify and bring it to your table so that you can go and buy it. So that's the concept of the Sewood relationship, which is kind of goes a step beyond what we have been looked at the example 2. In example 2, we looked at, based on the economically recoverable material, how much resources we have. And so there is a relationship, and that's in terms of the concentration of the material and the cost to refine the material. So that's our Sewood relationship, and we'll look at that. And it depends on technology. So as a technologist, as if you can come up with a better technology, working with your mining friends, metallurgy friends, mechanical friends, again, I have been telling you again and again that Mother Nature doesn't work in silos. Mother Nature always works as one entity. We have to look things in a systems perspective, and that's immaterial of whatever you do, like whether you are working in whichever field you will work later on in your career. You have to have a tendency to have a systems approach, like have the big picture approach of the whole, so that you don't solve problem here and then create another problem on the other side. So if you look at the big picture as a systems approach, then we can look at the things in totality. So here, if we can come up with a technology, and when we the technology these days cannot be just one discipline. There will be some automation involved, so computer science has to be there, the metallurgy people has to be there, the mining people has to be there, mechanical instrumentation, because there will be some instrumentation control. So lots of things, some software. So it's all the people have to come together, and then if we come up with a better technology, and as the technology becomes more efficient, the cost with the material extraction will go down, and then the cost can be reduced. So and then the concept of entropy comes. Remember, you heard about entropy. You have taken a course on chemistry where you talked about entropy, that certain amount of entropy must be overcome to purify the material, and that imposes a minimum energy burden that needs to be overcome. So if you look at this particular graph, this kind of tells you the metal prices as a function of dilution of the metals in commercial ore. So this is the dilution, the x-axis is dilution, the kg of ore per kg of metal, how much kg of ore is required to produce 1 kg of metal, and then here you see the price. So is smaller in this particular area, we have less number of kgs of ore is required. So for example, for iron, depending, again you see a line here because that depends on different technology. So for iron you can even start from so it's from like 1 point something nearly 2 to here around 3, 4, 5, 6, 7. So 2 to 7 kg of ore is required to make 1 kg of iron, and as opposed to if you go to platinum, you require almost 10 to the power of 6 to the range of 10 to the power of 7, and gold again you have 10 to the power of 5 to 10 to the power of 7 onwards. So again this line represents different technologies out there. So same thing with the silver, different technologies out there. So based on more and more ores required to produce 1 kg of the metal, more will be the price, and more it's a difficult, that's what the extractable reserve we have that we talked about earlier. So that's kind of gives you some idea about how these different kind of material that in terms of what is available in the Mother Earth as a total extractable material, and then what can be economically extracted. And for any extraction process, there is an environmental footprint, there is water required, there is energy required. So all those things goes in there. There will be some emissions coming out, and then we also have to look at what is economically extractable, and then how the price dictates in terms of this Sewood relationship that you just saw. So that was in the first part. So let's kind of look a little bit on the second part as well in terms of its. So second part is in terms of the material recovery. What is the energy burden? Again, don't worry too much about this text in the slides. It's just for you to read. Right now, I'll tell you that you just focus on the video part, the audio part, and try to understand what I'm trying to explain. That it's in terms of the energy burden of the material. It's we remember that delta S. We have to look at the estimate of the energy. So we calculate the entropy. So which entropy has to be overcome, isn't it? So if you have 1 kg of metal present at 0.2 ppm mole fraction basis of water, so we have to harvest this lithium from seawater to make lithium iron batteries. So we can calculate delta S, which is the entropy with the molar entropy of mixing, and then based on your gas constant, mole fraction, and atomic weight and all that. So this is what you have already done as part of some chemistry exercise. So energy burdens of the material can be calculated, and then the minimum energy required is we try to get the Gibbs energy. So that's the energy required to overcome the change in entropy. That's your delta G, which is the delta G is the Gibbs free energy, T is the temperature, and delta S is the entropy. So that you can calculate, and based on that we can find out like what are the like once we know the energy is required, we can find out lower the Gibbs free energy, more favorable will the reaction. So based on that we can find out which reaction among the different processes out there in terms of elemental recovery, elemental refining, which one will be more preferable. That depends on the Gibbs free energy. So that's again, whatever I said is already kind of is there on that text that is there in the slides, so you can read it and try to understand it again, but it's like don't get too much bogged down. It is not that difficult. It is just trying to give you some more detail in terms of these concept. So it's if a gallon of fuel, like if you have a gallon of fuel costing $3 and each gallon contains around 125,000 BTU, which is a energy, what are the energy costs to recover 1 kg of metal at room temperature and at 400 Kelvin? So we can find those kind of information on that particular aspect as well. So so that's in terms of the entropy part, in terms of how things has to be recovered. Economically recoverable reserve, there is a McElvery diagram, which is its amount of various elements in the earth crust that is present in high enough concentration to recoverable are limited, which we saw already. So the cost of material is not by only physical laws overcoming entropy, but by the technology used. Technologies are continuing to evolve, so the amount of energy that can be economically recovered today is different, maybe different than what it will be 10 years from now, because the technology may have evolved and we have better technology, so we may be able to recover some of these metal which we are not able to recover it today. So and the amount that is economically can be reserved is known as reserve, and they are defined in multiple ways. So if you look at this particular the reserve classification, that's the McElvery diagram, which is from USGS 2010 kind of like a report, where they looked at this cumulative production, which is like economic, marginal economic, sub-economic, and then there could be some other occurrences, non-conventional and low-grade materials. Then what are the identified resource, whether demonstrated, measured, indicated, inferred, undiscovered resources, what is the probability range in terms of hypothetical or speculative. So they have come up with this diagram where they looked at, okay, this is economic, means there is reserve available and there are inferred reserves, or we know the reserve is fine. And then marginal reserves, sub-economic means we have demonstrated sub-economic resources, although it is there, but it's at very low concentration, so that may not be a very effective way of doing it. So reserves, as we know, they are economically recoverable, which can be recovered at cost lower than the current price. So that's your economically recoverable. Reserves that are known and their extent demonstrated. Demonstrated reserves that could be cost effectively recovered through either moderate improvement in technology or increase are known as marginal reserve. So whatever is the technology today, if we improve the technology, we can even get the stuff which is there in marginal reserve, although the cost may be a little bit higher. Demonstrated reserves are unlikely to be recoverable at any foreseeable price, are referred to as sub-economic. Although it is there, but it would be too costly to recover it. So that becomes sub-economic. It's not economical to do that. And then so demonstrated reserve that can lead to inferences that similar geological formation may contain similar reserves. So that's your inferred reserve, and which can be economic, marginal, or sub-economic, all three. So because we are not sure that the reserve is there, but it is possible that since the natural conditions, the mineralogy and other things in this newer site is similar to the previous site where this particular element was very readily found. So those can be used for that. Some elements in terms of the supply, we have based on, there is again, when I say infinite supply, it's not really infinite, but means that for several years it is available. There are some for ample supplies, there is some potential adequate supply. We'll look at the bottom one, which is the potentially high limited supply. Silver, gold, copper ores, mercury, tin, zinc ores. So many of these we use, isn't it? Many of these we use for many of the our different usage we have, especially if a country like India, where gold is so much of a high demand for marriages per time and other purposes. People love to buy gold. So but the gold we have a limited supply, and then we have we have potentially like highly limited supply, then we have potentially limited supply with some other elements, and then we have adequate, ample and infinite supply. So multiple elements are present together in minerals. For example, copper ores typically contain arsenic, selenium, and other things as well. Platinum ores typically contains iridium, OS, these rare earth metals. The elements with the highest demand or highest price tends to drive extraction of these ores. So if you have a copper ore which contain arsenic, selenium, and Te, if the copper is more pricey, your focus will be on copper. The others may get collected, if it becomes as a byproduct, fine. If it's not, it may just get as part of the mining overburden. The problem with that is, if arsenic goes into the mining overburden, not extracted, arsenic will have a leaching issues, and those. So for example, mining of zinc produces cadmium. So there is another example here, that in terms of the economics, when you produce zinc, cadmium is produced as a byproduct. So although you are not really making any extra effort to get cadmium, since cadmium is available as a byproduct of zinc production, cadmium becomes cheaper, because there is no extra effort to recover cadmium. You get it as a buy one get one free, that we say in many of these supermarket sale these days. So when you go for zinc, you get cadmium as well. so that so you can have a cheaper price for cadmium because you didn't have to pay, you didn't have to make so much of an extra effort. But that's not always so that may not be always the case, but that's for all other elements. So materials, they have a life cycle, and there are extracted. We talked about that. Material can be reused and recycled. In addition, the different types of uses, the same material, okay, more and more we can recycle, reuse. We can have a significant impact on its environmental footprint. We can reduce its environmental footprint. Different types of usage of the same material can have different types of impacts as well. So we have to look at this flow of emissions of material, manufacturing, use. So in the next module, we'll try to look at some of these, how to track these materials in the engineered system. So far we have talked about in terms of its abundance. First of all, in terms of the abundance, how much it's out there, what is economically reserved, what is non-economical, whether it's there but may not be available, and then some of these which comes as it comes in it together. So we looked at all these different aspects in terms of the reserve. Now, once the material has been extracted, how it flows into the engineered system, that will be the focus of the next module that we'll take up after this. So thank you, and I hope that you're enjoying this course. Do keep us posted for any questions or anything you have through the discussion forum, and we'll be very happy to answer your questions. Thank you.